Hi everybody, this is Dr. Nigro with a new screencast for Chem calculations. This one is going to focus on drawing Lewis dot structures for covalent molecules. Now I realize this is not technically a calculation, but it is an area of chemistry that students do have difficulty with. So I figured outlining how to do it would be a good idea. All right. When I build my Lewis structures, I do so in a very systematic way. I follow a set of rules, I do them in the same order, and I do not skip steps. So I'm going to outline those for you in the area above, and then we're going to walk through those steps for the four molecules that I have below. All right. So whenever I'm given a covalent molecule, and remember, all right, covalent, oops, means all non-metals. All right. The first thing I do is tally up how many valence electrons I have to work with. Because remember, when we form bonds between atoms in a covalent molecule, they do so by sharing valence electrons. So we don't worry about the electrons inside of that valence shell, only those electrons that are on the outermost valence shell. So I'm going to tally up all the valence electrons, all right? And tally just means add up. And I do that by looking at the location of each element on the periodic table and using that group number to determine how many valence electrons we have, all right? Once I have that total value, then I'm going to draw what I call the skeleton structure. All right, and that skeleton structure is just the connectivity of the atoms to one another, and these can be relatively straightforward. Generally speaking, the element listed first in the formula is your central atom, and then all the other atoms are connected to it. Sometimes we have what's called a multi-center molecule, where you're going to have two central atoms. I'm going to do one of those for you. All right, for our purposes, at least in our chemistry class, we're going to focus on simple molecules. And if you have questions about connectivity, you're always welcome to ask. All right. Once I've drawn that skeleton structure, I'm going to subtract, whoops, sorry, 2 electrons per bond from my total. All right, because the bonds in that skeleton structure, they're formed from electrons, and those electrons had to come from somewhere, and they are going to come from our total number of valence electrons we have to work with. All right, once I've subtracted those electrons out, I'm going to then look at each element within that structure, and I'm going to determine whether they have an octet already, and if not, how many electrons do they need to gain an octet. So I'm going to check all atoms for their octet, which means 8 electrons. All right, now those 8 electrons can be in the form of a bond or in the form of lone pairs, right? All right, once I've checked all those atoms for octets, I determine how many electrons I need to fill octets. All right, so I look at what I have and I look at what I need and I make a determination. Do I have enough? So I determine how many electrons I need to fill octets, and then I compare to electrons that remain from number 3. All right, so in other words, the electrons that remain after I've subtracted them out when I form my skeleton structure. Just fixing that. All right, if I have enough, great. If enough, you're going to fill in those octets as lone pairs. All right, I'm actually, now that I think about it, going to add a structure because I don't have one. All right. If not enough, we're going to need multiple bonds. All right, and that means that we're going to need a double bond or a triple bond. All right, now, I don't have space here, but I'm going to add number 9 up here above. Once I'm finished, check your work. All right. One of the most frustrating things about grading Lewis dot structures is that it's so easy to check your work, and yet so many students forget to do it. All right. We do that in 2 ways. All right. We check the number of electrons in our structure and make sure it matches the total number we had to work with. And then we go back and we check those octets and make sure every element has that octet. Okay? All right, so again, tally up all the valence electrons you have to work with, draw a skeleton structure, subtract 2 electrons per bond from total due to that skeleton structure, then check all atoms for octets, determine how many more electrons I need to fill in those octets, compare that number to what remain from number 3. If I have enough electrons, fill them in as lone pairs, and if not, add multiple bonds, all right? And then finally, check your work. All right, so let's go down here and try this first molecule. All right, so I've got SiBr4. So off to the side, I list my 2 elements in the number, and I go to the periodic table and I look for each element. Silicon is in group 14, which means it has 4 valence electrons, and I only have 1 silicon. Bromine is a halogen, so it has 7 valence electrons, and I have 4 of them, so that means I have 28. So if I add those together, I have 32 electrons that are my valence electrons. All right, so those are all the electrons I'm allowed to use as I build this structure. All right, so I start with my skeleton structure. Silicon is listed first in the formula, so I put Si first, and then I just put the bromines around. I tend to do this symmetrically. All right, we're going to see in a later video that the shape is actually a little bit different than what I'm showing here, but for now, this is fine. All right, if you wanted to do it in the shape of an X instead, also perfectly fine. All right, now, as part of my skeleton structure, I have put in 1, 2, 3, 4 bonds. All right, and each one of those bonds contains 2 electrons. So that means that I have used up a total of 8 electrons in my bonding pairs. That's what my BP stands for. All right, so I need to subtract those out, which means that I now have 24 electrons remaining for my structure. Okay? Next, I'm going to check all my atoms for octets, which means I need to look and see if, as drawn in my structure, how many electrons do they have around them. Now, this is not the valence electrons. I've taken all their valence electrons and put them into a bowl, and I have 32 that I'm now spreading back around. All right, so if I look at silicon, it's got, here I'm going to change my color just so you can see, 2, 4, 6, 8 electrons because of those 4 bonds. All right, so silicon's octet is full, so it is happy, as I say, although atoms, I guess, don't technically have feelings, but maybe. All right, if I go instead and look at the bromine up here, it's only got this 1 bond attached to it as drawn, which means it has 2 electrons sitting there. All right, that's not an octet, that's only 2, so it needs 6 more electrons. So I move to the bromine on the left, same thing, 1 bond attached, so it's going to need 6 more electrons. The bromine down below, 1 bond attached, so it needs 6 more. And the bromine to the right, 1 bond, so 6 electrons. So I need a total of 6 plus 6 plus 6 plus 6, which is 24 electrons. All right, and I go check my total, and oh, yay, that's what I have. So I need 24 electrons, and they're going to go into my structure as lone pair electrons. And what does that mean? All right, well, it means they aren't going to be shared between 2 atoms. Instead, they will belong only to the bromine. So it's going to look like this for the bromine up top, like this for the bromine to the left, and then the bromine on the bottom, and then the bromine on the right. All right, so I had enough, so I don't need to worry about step 8 as I listed above. All right, but I do need to do step 9, which is to check your work. All right, so I do that in 2 ways. I count up the electrons showing in my structure. And remember, each line is a bond, so that counts for 2. All right, so if I start at the top, I'm going to have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32 electrons are showing. All right, and I go check And that is exactly what I had to work with in terms of my total valence electrons for the structure. So that's good. That means I didn't add in any extra electrons and I didn't forget any. All right. Second, I'm going to check my octets and make sure every atom has its octet. If I look at silicon again, it's surrounded by 4 bonds. That's 2 electrons each. So the silicon is happy. Each bromine has 1 bond and then 3 lone pairs. So that's 2, 4, 6, 8. So each bromine has an octet, which means that I have a good structure. All right. In the end, when you're finished, you should not have any electrons left. So make sure that your total is now 0. All right, so let's do this next one. All right, we've got pH 3. So start out the same way. I've got a phosphorus and then 3 hydrogens. All right, phosphorus is in group 15, so it has 5 electrons. Each hydrogen has 1, so I'm going to have 3 total. All right, and when I add those up, I have 8 valence electrons to work with in my structure. All right, so similar to before, I put phosphorus in the middle because it's listed first. And I spread the hydrogens around. And again, for now, it doesn't really matter how you put the hydrogens around the phosphorus, as long as the phosphorus is in the center and each hydrogen is attached to it. All right, now I put in 1, 2, 3 bonds, 3 lines, and each bond represents 2 electrons. So that's 6 electrons in those bonding pairs, which means I have 2 electrons left. Oh, it's not very much. All right, but I'm going to go check my octets. So I look at the hydrogen. Now, hydrogen has a single bond attached to it, which means 2 electrons, which you might say, oh no, that's not an octet. But you have to remember that hydrogen is one of our exceptions to the octet rule. The noble gas on the end of hydrogen's row is helium, and helium only has 2 electrons. So hydrogen's goal is to look electronically, at least, like helium, so it is perfectly fine with 2 electrons. So all 3 hydrogens with that 1 bond are happy. All right, now phosphorus has 1, 2, 3 bonds around it, so that's 6 electrons, but it wants 8. So phosphorus needs 2 more electrons. All right, so in total, I need 2 electrons to make this structure stable. So I go check my total, and I have 2 electrons, right? Which means that those 2 electrons are going to go in as lone pairs on the atom that needs them, which in this case is going to be phosphorus. So I'm going to put those 2 electrons right there. And that means in the end, I've used up all of my electrons. All right, now, again, because I had what I needed, I didn't need to worry about any sort of multiple bond. All right, so I'm going to check my work. First, I check the number of electrons, 2, 4, 6, 8 showing. So 8 electrons showing, and I check the total, so that's good. All right, then I'm going to go check my octets. All right, each hydrogen, as shown, has 2 electrons, which it is perfectly happy with, and then the phosphorus has 2, 4, 6, 8, which it is happy with. All right, so this is a good structure, not a good structure. All right, now you might ask, well, what does it look like when we do not have enough electrons? All right, and so for that, I'm going to actually go down below. I didn't put one of these in. Sorry about that. All right, and I'm going to use the classic molecule for this, which is CO2. All right, so we're going to do CO2's Lewis structure down here. All right, so again, just like we did before, we have a carbon and 2 oxygens. Carbon's in group 14, so it's got 4 electrons. Each oxygen being in group 16 has 6, so we have a total of 12. Add those together, and we're going to have 16 valence electrons to work with for our structure. All right, now, same as before, skeleton structure, oxygen, carbon, oxygen. Carbon goes in the middle because it's listed first in that formula. We've used up 2, 4 electrons forming these 2 bonds in our Lewis structure, our skeleton structure rather, which is going to leave us with 12 electrons to fill in octets. All right, so we go check. As written, each oxygen has 2 electrons because of that bond in the skeleton structure, so that means they need 6 more each. All right, the oxygen in the center has 2 bonds attached to it, which means it has 4 electrons showing, so it needs 4 more. So I need 16 electrons, but I only have 12. So I do not have enough electrons just to use lone pairs. All right, so what we say is if you don't have enough electrons, you have to add a bond. All right, so we pick a side, and it doesn't matter which one, and we put in another bond. And because of that, we have to go back and repeat our steps. So we added a bond, so we need to remove 2 more electrons because of this bonding pair, which is going to leave us 10 electrons. Then we're going to check our octets again. All right, the oxygen on the left still has 1 bond, which means it still needs 6. The oxygen on the right now has 2 bonds, so that's 4 electrons, so it needs 4 more. And then the carbon in the middle has 2, 4, 6, so it only needs 2 more. All right, so by adding that single bond, we went from needing 16 electrons to needing 12 electrons. All right, well, if we go check what we only have 10. So once again, we are short. All right, so we're going to have to add another bond. All right, now I tend to add my bonds in symmetrically, so I'm going to put the other one here. But if you put a triple bond on one side and a single on the other, that would be okay too. Don't forget though that you need to subtract out those 2 electrons for that added bond. So now we have 8 electrons to work with. All right, back to checking octets. All right, now our outer oxygen on the left has 4 electrons because of those 2 bonds, so it needs 4 more. The oxygen out on the right, same thing, 2 bonds, so it needs 4 more. The carbon now has 2, 4, 6, 8 because it's got 4 bonds attached to it. So it doesn't need any more. So now all I need are 8 electrons. So you can see that by adding a bond, we decrease the number of electrons we need by 4, all right, which is great. Now, that 8 electrons, that's exactly what we have. All right, so that means these 8 electrons are going to be used to fill the octets of the oxygens as lone pairs. We load them in just like this. All right, so I used up those 8 electrons in lone pairs, and I'm out of electrons, so I'm going to check to see if I have filled octets and used up the right number of electrons. So I start by adding up the electrons. I have 2, 4, 6, 8, 10, 12, 14, 16. So 16 electrons showing. And if I look, that is what I had to start with, so that is perfect. Now I'm going to go check my octets. All right, if I start with that central carbon, it's got 2, 4, 6, 8, so it's good. The outer oxygen on the left has 2, 4 from the lone pairs and 6, 8 from the bonds. The oxygen to the right, 2, 4 from the bonds, 6, 8 from the lone pair. So all the octets are full. All right. All right, now I'm going to go back up because now we're going to look at 2 different types of molecules. The first one is a polyatomic, so it's got a charge. The second one is what we call multi-center, so we're going to have 2 central atoms. All right, the rules are exactly the same. All right, so we're going to start with bromate, which is BrO3 minus 1. All right, so we've got bromine, and then we've got 3 oxygens. All right, so each bromine as a halogen has 7 valence electrons. Each oxygen has 6, but there are 3 of them, so that's 18. All right, and then we have the charge. All right, so this polyatomic ion has a minus 1 charge, which means it's got an extra electron. So because of the charge, we get 1 more electron. Now, if this were a plus 1, we would remove an electron, but because we have a negative 1 charge, the electron gets added. All right, so we add all this up, and we have 26 electrons to work with. All right, so skeleton structure is the same as before. The bromine's listed first, so you put that in the middle with the oxygens around it. Where you put those oxygens doesn't really matter. All right, we've used 2, 4, 6 electrons in our bonding pairs, which means we have 20 electrons left to fill in our octets. All right, so we go check for octets. The oxygens each have 1 bond each, which means they only have 2 electrons right now, so we need 6 for each of those oxygens. The bromine has 2, 4, 6 already, so it needs 2 more. So if I add everything up, I need 20 electrons. All right, and if I go check my total, that's what I have. Whoops, not a sad face, that's a happy face. All right, so that means that I'm going to use those 20 electrons in lone pairs and put them on each of these atoms so that they can have their octets. So each oxygen is going to get 3 lone pairs, and then that bromine will get a single lone pair. All right, now because this is a polyatomic ion, all right, we like to put that polyatomic ion in brackets like this, and then we list the charge on the outside. The reason we do that is if you just showed the skeleton structure without that charge shown, they wouldn't know where that extra electron came from. You have to tell them that it's a charged entity. All right, now we're going to check our work, so we're going to go back and count. We've got 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26 electrons showing. And if we check, that's what we had to start with. All right, now we're going to check octets. Whoops, I got rid of my bracket. Sorry about that. All right, and if we look at each oxygen, they have 3 lone pairs and they have 1 bond. So that's going to be 8 electrons for each oxygen. And then the bromine has 3 bonds rather, and 1 lone pair, which is also 8. All right, so this is going to be a good structure. All right, now for our last one, all right, and it looks complicated, but it's not too bad. We're going to follow the exact same rules. This time, instead of 2 elements, though, we have 3. So we've got carbon, and we've got nitrogen, and then we've got hydrogen, but we've got a total of 5 hydrogens. All right, so carbon has 4 valence electrons, nitrogen in group 15 has 5 valence electrons, and hydrogen has 1, but I have 5 of them. So I'm going to have a total of 14 electrons to use within this structure. All right, so the skeleton structure, this is where it gets a little tricky. All right, hydrogen never in between 2 elements. So I'm going to start by connecting the carbon and the nitrogen. All right, now the way the formula is written, the hydrogens that are attached to the carbon go with that carbon, and the hydrogens attached to the nitrogen go with that nitrogen. So I'm going to put 3 carbons around my carbon and then 2 hydrogens on my nitrogen. So that's going to give me a basic skeleton structure. Now, this is something we're going to be working on. You know, if you can kind of logic it out, but if not, you can always come ask me. Okay? All right, so I've got 1, 2, 3, 4, 5, 6 bonds within my skeleton structure. Each have 2 electrons, so that's 12 electrons that I used in my bonding pair. So I've got 2 electrons. Wow, I don't have very many left. Let's see how it goes here. All right, now we're going to go check our octets. So if we look at the carbon, it has 1, 2, 3, 4 bonds attached to it, each with 2 electrons. So it is happy. All right, each hydrogen has 1 bond, so it's got 2 electrons each, which make them happy. They have their octets. The nitrogen, however, has 2, 4, 6, because it's only got 3 bonds. So it needs 2 more electrons. All right, so all I need to finish the structure are 2 electrons. And if I look, that's what I've got. So I'm going to put those 2 electrons in as a lone pair on that nitrogen. All right, so it's going to look like this. All right, so it seemed a lot more complicated than it turned out to be. All right, we should check our work though. All right, so we go back and we start first by counting. So we've got 2, 4, 6, 8, 10, 12, 14 electrons showing, which is what we had to start with. All right, we then check octets. Each hydrogen is good because it has 2 because of the 1 bond. The carbon has 2, 4, 6, 8 because of the 4 bonds. And the nitrogen has 2, 4, 6, 8 because of the 3 bonds and the lone pair. So this is, again, a good structure. All right? All right, so that's a basic how-to for the Lewis structures. We're going to practice some more in class. All right? I'm going to come back in a second screencast, and we're going to talk about 3-dimensional shape. And then in a third one, we'll talk about polarity and intermolecular forces.